Okay, so this is experiment 3. We're going to take a look at standing waves. And standing waves are waves which are basically reflected back and forth. And as are reflected, they basically interfere with themselves. So we have a forward-going wave and a backward-going wave. In this case, we're looking at a wave on a string. This is a transverse wave. This is a mechanical wave, which is going to be created by basically a mechanism that vibrates up and down. At first, it's going to be at about 60 hertz. And you're going to adjust the frequency according to what you need to produce a standing wave. But essentially, the waves are created at this end. They're sent to the end of the string where they reflect, come back, and again, interfere with themselves. Now, the thing about a standing wave is only waves of a very particular wavelength will fit between the two ends, okay? Between the end where they're being generated, will also be reflections down here, and the opposite end off of where the string ends. Okay, so looking at standing waves, advance this, looking at standing waves, they're such that the wavelength has to be related to the total length of the string, okay, by some integer. Now, here's the fundamental mode, and this is really where we have our lowest frequency. This, therefore, has our longest wavelength. If you remember, the wave on a string, its velocity depends on the tension of the string and the mass per unit length of the string. So the velocity is going to be fixed. It is going to be set by whatever tension we put on the string, right? The wavelength, however, can be changed by changing the frequency. So if we change the frequency, we change the wavelength. In this case, a low frequency is going to give us a very long wavelength. Here, the actual wave itself is twice as long as a string, okay? But as long as it's related to the length of the string, here, 2 times lambda is equal to L, we're going to get a standing wave. We also can get a standing wave if the wavelength is equal to the length of the string, right? One way of thinking about this is we have wavelength equal to 2L, wavelength equal to 2L over 2, and the third harmonic comes from 2L divided by 3. So our wavelength is always equal to twice the length of the string divided by some integer n. N equals 1, n equals 2, n equals 3, right? So the wavelength progressively gets smaller and smaller as n gets larger and larger. All right, so we're going to do these, produce these standing waves, cause them to oscillate, cause them to interfere with themselves. And really what's happening here is we only get constructive interference for certain conditions. Any other wavelength that doesn't fit the way that I prescribed here is going to destructively wipe itself out, and we're not going to get these standing waves. So for instance, if my wavelength is a little bit more than twice the wavelength or a little bit less than twice the wavelength, length of the string, destructive interference will result, no standing wave. Same thing here. Here, our wavelength is equal to the length of the string. If I'm a little bit higher in frequency, which is going to create a shorter wavelength, or a little bit lower in frequency, which is going to create a longer wave, those will cause the waves to basically interfere destructively and be wiped out. Okay? So, effectively, what I'm doing is adjusting the wavelength so that only a certain type of wave can fit between these 2 points. Now, there are a few important features of these standing waves. The points at which they're not moving are called nodes. There are always 2 nodes at the end. And ideally, this end would have no motion whatsoever, but in actuality, the little vibrating arm is going to move the string to that location. So there's kind of a node there. We pretend like it's there. So the fundamental 2 nodes at the end, that's all it has. At the center, we have an antinode where the string is vibrating the most. Now we go to the n equals 2 with the second harmonic, okay? Now we still have our nodes at the end, but notice there's also a node at the center, right? 2 antinodes, 3 nodes, 1 node at the center. N equals 3. 3 antinodes, 3 loops if you want to call them loops, 2 nodes, okay, in the center, and 2 nodes at the end. An easy way to recognize what type of standing wave you're looking at is simply count the number of antinodes. Our n equal 1 has 1 antinode. Our n equals 2 has 2 antinodes. Our n equals 3, it has 3 antinodes. But again, the relationship is that the wavelength is equal to twice the length of the string divided by n, which is which harmonic or which n we're looking at. And again, this is nice because this actually illustrates in slow motion how these transverse waves would look. We notice with the fundamental, look how slowly it's moving, okay? This is the lowest frequency. This is the longest wavelength, all right? Now for the first part, we're actually going to operate all at the same frequency. For this case, all the tensions were kept constant. This would be pretty close to what is going to happen in the second part of the experiment, okay? But you notice here that the frequency of the second mode, the n equals 2, is twice as much as the frequency of the fundamental. The frequency of the n equals 3, okay, is 3 times that of the first. So there's a very definite pattern here. The wavelength is inversely proportional to the n. The frequency, in this case, because we're not going to change the tension, is proportional to the n. That becomes very important later on. But again, here's our n equals 1, n equals 2, n equals 3, n equals 4, and we're going to go all the way up to n equals 5. All right. So once again, you're going to set the experiment up, and we're going to go some fixed distance. I'm going to choose something very convenient, like 1 meter, close to 1 meter. That's my L. And again, the wavelength is going to be twice the length of the string for the fundamental, or we can say the length, usually we use capital L, is equal to the wavelength divided by 2. Again, you can see how these integers come up. And L equals 2 times lambda over 2. L equals 3 times lambda over 3. If we look at the wavelength, we invert these fractions, and we get the wavelength is equal to 2L. The wavelength is equal to 2L over 2. The wavelength is equal to 2L over 3 and 2L over 4, so on and so forth. So here's actually what it's going to look like. We have the little vibrating arm over here. This is what is putting energy into the string, causing it to oscillate. And ideally, the node should be right about here, okay? Here you can see the fixed end of the string. This does not move, so that is held fixed. But this is our n equals 1, and we can see how there's a big fat antinode in the center. As we go to the higher modes, what we notice is the amplitude isn't quite as big. And we also notice that there's not a perfect node at the center. This oftentimes will happen when our frequency isn't perfect, or on this end right here, we don't have a perfect node over there. And there's the n equals 3. N equals 4 obviously would have 4 antinodes. N equals 5 would have 5 antinodes. Okay, so for standing waves on a string, the length of the string we're going to call L, all right? And we basically say that lambda is equal to 2L divided by n. We can also say that the frequency, if we hold the tension fixed, will be equal to some integer n times the fundamental frequency. Again, for the first case, tension is the one that's being changed here. But for the fundamental at a particular tension, any of the higher harmonics are just going to be some integer value of this. okay? And again, you can see the relationship between frequency, the length, and the tension, and the mass per unit length. All right, what are we doing for this experiment? Well, we're actually combining three different equations, okay? We're looking at this first equation, the speed of the wave, okay? We're looking at this equation right here. I'm going to try to draw it here. Let's see how well I do with this. The speed of the wave. That was terrible. Let me try a box. That might work better. Let's try a box here. So we have this first equation, the speed of a wave, right? It says here that the velocity is equal to the wavelength times the frequency, okay? That the speed of the wave is basically fixed by whatever medium it's traveling through. For our wave on the string, the tension of the string and the mass per unit of the string really sets what the velocity is. So if I change the right-hand side of the equation while holding the left-hand side of the equation fixed, that change must not have any impact on the overall value. What do I mean by that? I didn't really word that very well. If I increase the wavelength, the frequency needs to decrease. If I decrease the wavelength, the frequency needs to increase. Okay, so that's simple enough to understand. The other equation that we are going to use here is this middle equation right here, which is the speed of a wave on the speed of a transverse wave on a string. It says the square root of the tension, and for this experiment, we're actually going to hang a mass off, so the tension is actually going to be mg in this particular case. The velocity is equal to the square root of the tension divided by the mass per unit length. Okay? By the way, folks, I've already determined the mass per unit length for you, and it's 3 times 10 to the minus 4 kilograms per meter. Okay, 3 times 10 to the minus 4 kilograms per meter. So this right here that's been determined for you. Normally during the lab, students are asked to cut a length of string, put it on a scale and measure it, but because the mass is so small, we don't get a very accurate measurement. So instead, what I've done is I've cut out a 10-meter long string, measured it to be 3 grams, and just with a little math, converting grams to kilograms, we get 3 times 10 to the minus 4 kilograms per meter. All right, so again, I'm not going to draw that out, but let's use a different color here for our last equation. And again, for standing waves, we've already said this. The wavelength of the standing wave is going to be twice the length of the string divided by n. So in this lab, we're actually going to combine all 3 of these equations. Okay? I'm going to put them together and use them to find an expression which relates tension, the mass per unit length, the frequency, okay, and also the integer n. Okay, we're going to put them all together and use that to solve. Hey, it was supposed to clear everything. Didn't want to clear everything. There we go. Now it's clear. Okay. So again, we're combining 3 of these equations. If we put them together, we can come up with this expression right here, the center equation right here, that says the square root of the tension divided by the mass per unit length is equal to twice the length of the string divided by the integer n times the frequency. Okay? This is going to be very important for our first experiment, because what we're going to do is that we're going to graph tension as a function of 1 over n squared. And when we do that, we'll get a slope which is related to mu. Now, I've already measured the value for mu. Again, it's 3 times 10 to the minus 4 kilograms per meter. And we're going to use that to try to see if this equation gives us the correct value. Now, we're going to do this by actually graphing again. We're going to graph tension as a function of 1 over n squared and use the slope to then come up with an expression for mu. In the second part, instead of changing the tension and doing tension as a function of n, we're going to do frequency as a function of n. We're going to change the frequency while holding the tension fixed and look at this slope and find out what mu is from that. Okay. Part 1 of the experiment. What you're doing here is, again, you're hanging, basically what you have is you've got a pulley and then you've got a mass, which you hang off the side here, and the tension in the rope is equal to mg. Okay? You're going to keep adjusting that tension so that you can get each of the standing waves, the n equals 1 through n equals 5. All right? Now let's look at this equation over here. Yeah, and I'm going to start annotating, so just give me a moment and let's see what we have. Again, here's the equation I'm starting out with. The square root of the tension divided by the mass per unit length, it's a little bit hidden right here, equals twice the length of the string divided by the integer n times the frequency, okay? We're going to hold the frequency at 60 hertz, so that doesn't change. We are going to change the tension to get different values of n. Okay, so let me rewrite this equation, and I'm going to change it just a little bit so that tension becomes a function of 1 over n squared. So now our new equation looks like this. Okay? Notice we have tension on the right side, and we have 1 over n squared. I'm sorry, tension on the left side, 1 over n squared on the right side. And if we graph tension as a function of 1 over n, tension on the y-axis, 1 over n squared on the x-axis, okay? Mu times 4 times L squared times F squared. It's pretty complicated looking, but it's not too bad. But the mass per unit length times 4 times the length squared times the frequency squared. Again, the frequency is going to be 60 hertz. That becomes my slope. Wow. Well, how do I find mu from that? Well, again, you're going to graph this. The computer's going to find the slope for you. And using that slope, you can then manipulate this equation. Slope is equal to mu for L squared, F squared, okay? Manipulate that to solve for mu, okay? I'll just divide both sides by 4L squared, F squared, on both sides. And mu now becomes equal to the slope, okay? Mu now becomes equal to the slope divided by 4L squared, F squared. Okay, so do your run, keep changing the tension to get the different values for the standing waves. By the way, this kind of goes backwards. N equals 1 is way up here. N equals 2 is here because we're graphing 1 over n squared. N equals 3 is here, n equals 4 is here, and if you're lucky, you might even get an n equals 5. Okay? That slope gets plugged into here. Divide by 4, L is going to be about 1 meter. Frequency is going to be 60 hertz. Okay? That'll get you your first value for mu. And you're going to do a percent difference. You're going to do a percent difference between the value that you get and 3 times 10 to the minus 4 kilograms per meter, because that's what I got by putting the string on a scale. Okay? So that is our first part of the experiment. Okay? Or at least this is the theoretical part of the first part of the experiment. Again, where you're graphing one variable, okay, you're graphing tension, and and you're doing that as a function of 1 over n squared. Okay? Find the slope and plug the slope into this equation. That will give you mu. And again, as you do the data, if you forget this, you can come back to this presentation, and that has the equation. All right, let's erase everything and go on to the second experiment. Okay. Now, first experiment, you were varying tension, okay, while keeping the frequency fixed. Now you're going to vary frequency while keeping the tension fixed. All right? Now, in this case, it's a little more straightforward. I take my equations from the 3 combined equations. I get that frequency is equal to 1 over 2L times the square root of the tension divided by mu, okay, times n. So I'm going to graph frequency on my y-axis and n on my x-axis. All right? My slope of this equation right here is in red, is equal to 1 over 2L square root t over mu. I'm trying to solve for mu. So mu becomes t over 4L squared slope squared. Okay? So whatever value I get here, I plug into this equation right here. And I can find my mu. Compare that again, percent difference, to your measured value, which I did for you, 3 times 10 to the negative 4 kilograms per meter. Okay? That's basically it. And again, the whole idea of this experiment is you're really testing these 3 equations right here. Okay? You're really testing these 3 equations. If this is valid, this is valid, this is valid, your measured value for mu should compare well with your experimentally determined mu that you got from the 2 slopes. All right?